One way to solve a system of linear equations is using a matrix method. So what we're going to do is use the coefficients of these equations and place them in a table or a matrix. We can see here that the equation in blue, x minus y plus z equals 5, has a series of coefficients which are 1, -1, 1 and 5. And if you follow the equations through for the next two, you'll see that the coefficients there in the second equation match row 2, and the coefficients of the third equation, -12, -6 and 3, match the third row of the matrix. You'll also notice that the constant values on the right hand side of the equations, 5, 2 and 9, comprise the last column of the matrix. Now what we're going to do is apply the same principles of solving simultaneous equations, but use row operations in the matrix so that we can actually come to a solution. If you think of solving simultaneous equations, what we do is normally eliminate the x value or other variables, and then go through and reduce our equations to two variables, and then ultimately eliminate another variable so that we can get down to one variable solution, which we can then substitute back into the other equations. In terms of the matrix, what we're going to do is a series of row operations. So let's look at how we go through that to eliminate some of the variables. Our first step is to try and get zeros in row 2 and row 3 in the very first entry. And we're going to do that by a row operation, which is to take all the values in row 2 and subtract 4 lots of the values in row 1. You can imagine then what we'll effectively have in the very first entry is 4 minus 4 lots of 1. And we'll worry about the other entries in a moment. What we're also going to do is aim to have a 0 in the first entry of row 3. And we do that by going 1 lot of row 3 plus 12 lots of row 1. Again, effectively what happens there is we'll have -12 at 12 lots of 1, resulting in a 0 in the first entry. It would be wise to pause here to see what would happen if we go through and do the row operation that everything in row 2 becomes what was previously there minus 4 lots of the value in row 1. Likewise, row 3 becomes what was previously there plus 12 lots of the value in row 1. So pause here and see what results you'd actually obtain. So by doing those row operations, this is the resulting row 2 and row 3. You'll notice now we've got zeros in the first entry. Our next aim is to get a 0 in the second entry of row 3. And we can see here that we've got -18 in the second entry of row 3. And if we add 3 lots of row 2, what will happen is that second entry will become 0. So same again, it would be wise to pause here, apply the row operation that you can see, and see what your row 3 will end up being, and see if we can get a match. So our third row becomes 0, 0, 15, 15. Let's think about what this matrix means in the context of our original equation. We've changed things a little bit. So we've still got our first equation, which is x minus y plus z equals 5. The coefficients match the first row. But the second row is now saying 6y equals -18, and the last row is saying 15z equals 15. So from this matrix arrangement, we can actually solve the equations very quickly. We can see that z equals 1, y equals -3, and if we substitute those values back into the first equation, with a little bit of work, we can find out that x equals 1. So by manipulating the matrix, we're able to solve the equations quite quickly without going through all the process of including the variables. So this process has shown you a way to reduce the rows of the matrix whereby there are zeros in the bottom left-hand corner. So our aim is to get 2 zeros in the third row, the first and second entry, and a 0 in the first entry of row 2. Whilst there are variations to that, that's the simple aim, and by doing that you can then solve your equations using the row-reduced matrix. So what does that all mean? Well, the equations that we had at the start of this question represent planes in space as opposed to lines in 2 dimensions. And we can see here from this video footage coming up that we have a point of intersection of the 3 planes. The planes actually cross over at a number of points, but there's only one point which is an intersection of all 3 planes together. And we can see here from our solution that's when x equals 1, y equals -3, and z equals 1.